So we were discussing how to use a capacitor, make it seem like a battery. And we were also focusing on what are the constraints on the values of the capacitor, under which circumstances we can use a capacitor as a battery. And we saw that in case of our common source amplifier, we can manufacture that biasing voltage by using a resistor divider. And then we also saw that if we connect directly an input here, this will not suffice simply because the quiescent voltage at this node will go to 0 because the quiescent voltage of the input is 0. So one way to go about fixing this issue was essentially to put a capacitor. If I put a capacitor here, in the absence of an input, for example, if the input is not there, the capacitor automatically gets charged to the requisite voltage value, which was in this case, I think 2 volt or 3 volt. I don't remember, but something like that. And now I can use this other terminal, other plate of the capacitor, which I can use to drive the input. So another way of thinking about whatever we did in yesterday's class is the capacitor blocks the DC, right? It by virtue of putting a capacitor, it's not allowing the DC current to flow, and hence the quiescent point at this voltage at this node is not disturbed. Quiescent point is essentially all DC. So the capacitor doesn't disturb the DC, but it allows the AC input to flow through. So for non-DC inputs, the capacitor acts as a short circuit, provided we size the capacitor appropriately. And for a DC input, it acts as an open circuit. That's regardless, right? Because for DC, any value of capacitor will behave like an open circuit. Okay, and then we said that how do we know what value of capacitor should we use? Can we use any value of capacitor? Because if the capacitor is supposed to behave like a short circuit, does that mean it is regardless of the value we use? Then we saw that it's not the case. It's actually dependent on the RC time constant associated with the capacitor. And then we saw that if we only focus on this part of the network, because that is the part that is effectively setting the bias point. So this is nothing but this. And when we are talking about what is happening to an AC input, essentially what we are saying is what is happening when only this input is applied, that is, let's say Vp sine omega naught t is applied, and we are not bothered about what is happening to the other input. Other input in this case means whatever the voltage is, or whatever the voltage supply is, because this is a linear network. I can deal with each of these inputs, that are the DC, VDD and Vp sine omega naught t separately. So we use that to our advantage. So if we are only interested in figuring out what is going to happen to this, how will the capacitor behave in the presence of input having a frequency of omega naught, I don't have to bother about what is whether the VDD is present or not. So VDD I can short. So this R1 and R2 come in parallel. So this is effectively a Thevenin impedance looking into this node, right? The Thevenin impedance looking into this node is R1 parallel R2. So all we have to then figure out is what is the time constant associated with the capacitor, and the time constant is C times R1 parallel R2. This is the time constant. And then we saw that the constraint that we need to impose is the time constant has to be what? So this time constant C R1 parallel R2 has to be much, much greater than 1 over omega naught. If we satisfy this criteria, then essentially the capacitor acts as a short circuit. Another way of thinking about it was the fact that, if C goes to the other side, which is R1 parallel R2, is much, much greater than 1 by omega naught C, this is another way of looking at it. That is, as long as the impedance given by the capacitor is much smaller than the impedance given by the set of resistors, then for the frequencies of interest, the capacitor is as good as a short circuit, right? So that is being conveyed by this inequality. Okay, so essentially the story is the same, just the point of view of looking into the same story is different. And at times you will find that attacking the problem from the perspective of time constant is easier. At times it might make sense to attack the problem from the perspective of impedances. Okay. The last thing that we ended up with in the previous class, which we will do in today's class, is to draw the sinusoidal steady state waveforms, right, in frequency domain. As in, I would like to plot, for example, in this case, what should, if I say this is Vg omega, right? So I would like to plot what Vg of omega would look like if I vary omega naught. Okay, so essentially what I'm saying is, if this is my effective network, R1 parallel R2, C. This is some input Vi at a frequency omega. I would rather j omega, that's the usual nomenclature. And if I want to plot or Vg of j omega, whatever it should look like, then I would get two plots, right? I should get a magnitude plot and I should get a phase plot. Okay. So even before going there, what will the expression look like? This is something that we did yesterday. Vg of j omega only in the presence of one source will be j times omega times c times so let's do it fully. So this should look like R1 parallel R2 by R1 parallel R2 plus 1 by j omega c. So this would be j omega c times R1 parallel R2. Pardon? Yeah, right. So this should be Vij. Correct. Thank you. Okay, so now what I would like to do, I would like to plot this. I would like to plot this expression with regards to its magnitude and phase, and then try to get another. Basically, we are looking at the same problem from multiple different angles. We would like to look at the same problem from the perspective of how it looks like in a plot where I am plotting the phase and the magnitude with respect to omega. Okay, so let's do that. So if I plot, so whatever is mod of Pj j omega, first the expression will be, let's say I plot the transfer function. So this becomes omega c okay. So if I plot this, what should it look like with respect to? So are you guys familiar with dB? Right. So okay. So I'll be plotting this side omega in log scale. I'll be plotting this side. Let me call this h. We're plotting mod of h in log scale. Right. So this is also in log scale. This is also in log scale. So what do you think it will look like at low frequencies? Hold on 1 second. Yes. Right. At very low frequency, it should this term should dominate. Right. At very low frequency, this term should dominate. So essentially, it will be log of omega c R1 parallel R2. But if I am plotting in terms of dB, it will be 20 log of that. And if in a log-log plot, what will it look like? Straight line, great. So it should look like a straight line. And then at very high frequencies, right? What should the plot look like? Constant with a value of 0 dB, right? 1 in absolute scale, 0 in log scale. So it should look like this. Sorry, I should not interpolate. So this is here, and this should look like this. Okay. So when I say much lesser than or much greater than, right? So this is at a very low frequency. This is at a very high frequency. When I say very low or very high, again, it's with respect to something. It is with respect to what? Right. It is with respect to 1 over. It is respect to basically when the denominator becomes negligible. Denominator is essentially 1 or omega square c square r1 parallel r2, right? So essentially the break frequency is so whatever this frequency will be, this is 1 by c times r1 parallel r2, which you see is nothing but 1 by time constant, right? So as long as we are much higher than 1 over time constant in this first order circuit, it is we are in the flat region of operation in terms of the frequency, in terms of the magnitude plot. And here we are in a linear slope. What is the slope? What is the value of the slope? In terms of dB per decade, plus 20 per dB per decade, great. So this is plus 20 dB per decade. So now let me ask you this. Are you aware of Bode approximations? Okay, what does it mean? Yeah, so 3 decibel per decade comes later, but a very crudely, so let me paraphrase. So if I have to go from here to here, so ideally it should look like a smooth curve, right? Something like this, right? So what is Bode approximation? Bode approximation is essentially telling us that, I mean, I don't want to go into the smooth curve business. I will do piecewise linear approximation. So as long as, so just like we did an approximation here, right? So when we are much higher at a frequency which is much higher than the corner frequency, it's a straight line, which is horizontal. And as long as we are much lesser than that 1 over tau, the corner frequency, it is a linear line with a slope of plus 20 dB per decade. What Bode approximation is effectively giving us permission to do is to say that I will not bother about much less, much greater. As long as it is lesser, then this goes like this, and as long as it is higher, this goes like this. And wherever these two curves will meet, will be that frequency of pole, or in this case, yeah, in this case, it's basically the pole frequency where these two curves meet, and that curve is meeting at, in this particular case, as you see, at a frequency of 1 over time constant. Okay, so you will see that Bode plot will make will be an integral part of this course later on, right? Probably another 10 lectures down the line, where this type of approximations will be super useful. Okay. Okay. Any questions till now? You mean this part? Okay. So at frequencies of at very low frequency, how do you approximate this? Yeah, when much more frequency, so then it becomes omega r1 parallel r2. And you take 20 log of that. So it becomes 20 log of omega. You are plotting with respect to omega. So it's essentially a straight line of 20 dB per decade. Okay. Okay, fine. So similarly, we can also plot the phase. So what should phase look like for this? So let me also write out the expression for the phase. So what should be the expression for the phase? So this is the complete transfer function. Yeah, so the denominator, phase of the numerator minus the phase of the denominator. Phase of the numerator is 90, no real part, only imaginary. And phase of denominator is tan inverse of whatever, coefficient of j divided by coefficient of real, that minus this. So pi by 2 minus tan inverse omega c R1 parallel R2 will be your phase. And if I plot this, what should it look like? It should start from pi by 2. And then eventually end up with 0. And at that corner frequency 1 over tau, we'll have a phase of how much? Pi by 4. Okay. Okay. So when we typically say that we will be plotting the sinusoidal steady state response, we essentially mean that either we plot both the magnitude and the phase. But you will see later on in the course that there are ways of figuring out how a circuit will behave by only looking at the magnitude response also under certain conditions, right? So those will be dependent on the assumption that we know the phase response. We'll know the phase response as long as we know the magnitude response, because the location of the poles and the zeros are also dependent on, the way the poles and zeros affect your magnitude response, it will also affect the phase response in a certain known manner. Okay, so it is important to understand. It is we'll deal with this in more detail later on, but this is just a preface. It is important to understand how the curves will look like if we have 1 pole, 1, 0, 2 poles, 1, 0, so on and so forth, right? Have you done this in 200? You have not done this? Okay, then I'll probably spend more time.
The positive mark is perfect.
Okay. So are you comfortable with this part? So what is that frequency? 1 over C TNL, R1 parallel R2. That is the 3 dB frequency essentially, right? Where the magnitude goes to 1 over root 2. You know this?
Yes.
Okay. So similarly, at 3 dB frequency, what happens to the phase? The same thing, right? You just plug in the values, the same value, you put in the frequency, you'll get pi by 2 minus pi by 4, the phase drops away. That's all. Okay. Okay, fine. So this is as far as doing a brute force maths is concerned. But if I have to look at it from the perspective of purely circuits, right, and try to figure out how this system will look like without even writing the equations, what should I look for? So firstly, we understand that it is all about time constant, right? In a first order circuit, it is all about time constant. So when I say, when we are in a first order circuit, anybody tells you we are dealing with frequencies, much high frequency, much low frequency, intuitively what they are telling you is that much high frequency with respect to 1 over tau, much low frequency with respect to 1 over tau. So when we say in this case, I am dealing with a very low frequency, all I am saying is the impedance given by the capacitor, right? The impedance given by the capacitor is much higher than the impedance given by the resistor. At very low frequencies, capacitor gives you high values of impedances with respect to whatever it is attached to. In a first order circuit, it is attached to a resistor. Okay, so if the capacitor is giving you much larger value of impedance, so what impedance effectively, approximately, what is the impedance that the source is seeing looking into this side? Is the question clear? It is only seeing the capacitor's impedance, right? Effectively, because the capacitor is giving you almost the entire impedance. So the impedance that the source is seeing is 1 by j omega naught c, approximately. So if the source is seeing that much, what will be the current? Approximately, this current will be approximately. Basically at very low frequencies, capacitor dominates, right? Because it's in series. So capacitor dominates. Effectively, the impedance is 1 over j omega naught c. So the current will be j omega naught c times Vi, right? So if the current is that, this current is flowing into R1 parallel R2. So what will the voltage that you will develop here? R1 parallel R2 times j omega naught c times Vi, right? So at very low frequencies, this is what this should be the response of this should be the sinusoidal steady state response of the circuit at very low frequencies. And that is what we also saw from that equation. But we are trying to get an intuition as to how to go about figuring out what's going to happen without writing out the full-blown equations, because that will be helpful later on. At very high frequencies, what's going to happen? So the capacitor will almost act as a short circuit, and the entire Vi will come to across the resistor, right? So this happens at omega much less than 1 over tau, and at omega much greater than 1 over tau. This is V naught, right? Your V naught will be here. And so by looking into these two approximations, you already know how your Bode plots, essentially, that phasor, that magnitude plot will look like, right? So simply by looking at these two approximations, I know that if I know 1 over tau, I know at much lesser than 1 over tau, somewhere in this region, our plot should look like this, because this is the equation. And when I'm at much higher frequency than 1 over tau, it should be a flat line. This is, I'm plotting obviously mod of V naught over Vi. And since I know this is the first order circuit, and I have two slopes, I know those two slopes will meet. Two slopes will meet at the corner frequency, which is a 3 dB frequency. Using a Bode approximation, this will be a straight line. Right? So I am spending some time on this because we will be using such intuitions to figure out, to plot the magnitude responses later on, right? Using these simple principles. Okay. Any questions? Okay. So then let's proceed. Yes. This is also a log curve. I mean, when we plot magnitude in this course, always log curve. So this is essentially 20 log 10. And this omega is also in log scale. Okay, so this was again, this was a common source amplifier. So we took care of how to connect the input by doing whatever we did till now. But there is another issue with the output. The issue is not evident till now, but let me make the case for it. So the issue is very often this RL is not an explicit RL. Okay, so this RL can be reference to something else, It can be, for example, when you take the example of the speaker, right? So you have a amplifier which pushes a diaphragm, right? So you have an amplifier which generates some electromagnetic wave, and you have a magnetic diaphragm which vibrates, and based on the vibration, you get a sound wave. So there you don't have an explicit RL, obviously. There is no effective, no resistor connected to it. The way we model the resistor is the fact that your amplifier is pushing out some power, and the acoustic waves are catching the power, right? There is a transference of power from electronic to the acoustic domain. So when you equate these two powers, essentially and you translate that power in electronic domain, you will get some V squared times some effective R, because power means some V square over some effective R. Power means if you have a voltage, there has to be R, otherwise there is no power. So it's not an absolute resistance, it's a model resistance. So from what I essentially mean is that you don't have this effective RL. That RL is a model. So that is an example. Another example can be, you have one amplifier driving another amplifier or another stage, where this RL again is probably a modeled input impedance of that stage, not an effective, not an explicit RL. So then how do you go about arranging that RL in the fashion that we have? Because the way we have connected this RL, it is serving two purposes. It is helping us bias the transistor, and it is also helping us getting an amplification. Okay. So if the RL is not available in this form, then you cannot really do anything about it. Right? So which means that I have to use some other resistor for the biasing purposes. And then an RL is an implicit RL somewhere else. This RL sits here. This RL is not there. And you have to assume again, this RL might not be an effective, it's not an absolute RL. It can be a small signal RL, it can be a modeled RL, it can be some input impedance of the next stage through which you cannot pass the DC current. Okay. So now the problem statement gets modified to, how do I get an amplification between this VI and I want a voltage V0 across the RL? Small signal voltage V0 across RL. Okay. So firstly, we need this one, because let me now call this RD connected to the drain. We need this one because if we don't have that one, there is no way I can pass this entire small signal current into the RL. Right? So we have to connect something between, we have to connect something here so that the small signal current, the signal current that flows through the device M1 goes into the RL. Yes. Okay. So let me get rid of RD for the time being, then we'll see. So if we don't have RD and we want to get a voltage across RL, is it possible to get it? No, right? Because ultimately, whatever current that comes through the device M1 will always prefer going into the short. Okay. So which means that I have to put something there. And I mean, the most convenient thing to put is some resistor RD, because you already know, right? That works. So now the question is, if I develop the incremental gain between V0, which is across RL, and VI, what should I put between these two contraptions in order to get this? In other words, what I'm saying is, so this device is going to give me a current which is IDQ, which is the biasing current, which is anyway that is present, but it's going to give me some extra current. And that extra current is how much? In the presence of VI, and assuming the capacitor acts as a short circuit, if this capacitor acts as a short circuit, what will be the voltage here? Incremental VI. If this is incremental voltage VI, what will be the incremental current through M1? Y21 VSG. So in this case, I should simply write it as minus Y21 VI. because source is incrementally grounded, right? So all I want is to ensure that incremental current flows through RL, right? That is a requirement if I want to get the gain across RL. So I want this incremental gain to flow, incremental stuff to flow through RL. So how should I connect these two? I don't want any IDQ to flow through RL. Yeah, so basically capacitor, right? That's what we have been doing. So put a capacitor. Let me call this C2. So I want all the again, let's assume that the capacitor is infinitely large. The capacitor is infinitely large. It doesn't give me any voltage drop if current flows through the capacitor. But having infinitely large capacitor is also not sufficient, because I want all the incremental current to flow through RL. But now it's an RL parallel RD. Right? If C2 is infinitely large, which is effectively short at signal frequencies, then the load that the transistor is seeing is RD parallel RL. So what is an additional constraint that needs to be imposed? RD should be much greater than RL. Excellent, right? So one is RD definitely should be much greater than RL. This is to ensure all incremental current flows through RL. And the second condition is C2 has to be infinitely large. C2 has to be infinitely large. But now we know better, right? C2 need not be infinite. What should C2 be much more than? Think time constant. Yeah, right. So if I have to look at the circuit, so it should be, so essentially what I'm trying to get at here is what is the time constant associated with C2. So if I have to find out the time constant associated with C2, so let's do that explicitly. So this is biased. And I can assume the input is shorted, right? Because when I'm trying to figure out the time constant associated with it, so at that time, let me assume that I have, even if you don't assume input to be shorted, it's not the problem. The capacitor is shorted is not the problem as long as the input is shorted, right? So essentially, this side is not moving at all. But now I have to figure out what is the time constant associated with the capacitor. So I need to figure out what is the resistance looking into this node. Because the other side I know that is RL. I need to figure out what is the resistance looking into this node. Now, resistance looking into this node, I see two, right? One is looking, this side is RD. That is quite evident. What is the resistance looking up? How when I'm talking about resistance looking up, I'm talking about incremental resistance looking up, because everything is incremental. Pardon? 1 by? Yeah. 1 by? Y21. Why Y21? So let's replace this incremental equivalent of the transistor, right? That's the best way to go about it. So if I replace this, what should I get? Input side. So let's draw the full-blown replacement. This is the gate. Okay, so what is source? Source is grounded. So this becomes Y21 times minus VG. What is VG? So we are trying to figure out what is the impedance, right? What is the impedance looking up? So what I'll do, I'll put a test voltage here. So let's get rid of this. So we are putting a test voltage here. So what will be the VG? Okay, this question is why are we doing incremental domain for the equivalent resistance, right? So the reason we are doing incremental is because we are everything. So we are essentially interested in finding out the small signal gain. Ultimately, everything is small signal, right? So we are effectively trying to figure out what will be the change of voltage across RL if I have a change in voltage in VI, right? So since we are only interested in increments, effectively the resistance that we are also trying to figure out is incremental resistance, right? So everything is incremental, that's why. Okay. Yeah, VG is zero, obviously, right? Because, I mean, in order to have VG, anything to be non-zero, some current has to flow through this, right? Some current has to flow through this, but there is no way that current can flow out. So no current can flow through this. Effectively, impedance looking in this side will be infinite, so no current will flow through this, so VG will be zero. So if VG is zero, so essentially this goes off, right? So what is the impedance that you see looking up? What is the impedance looking up? Infinite, right? So looking into the drain of the transistor, which is in saturation, you get infinite impedance, right? Does that make sense? Yes. You mean the left side? Yeah, that will be shorted in single frequency. That's true. We can as well short it, but even if you don't short it, it will come. Right? Yeah, but your point is well taken. I mean, since we are talking about single frequencies where we assume the capacitor to be shorted, we should be shorting the capacitor. Yes, ideally we should. Yes. Yeah, question. We took BT0 why? So you tell me what is the current to this underlying condition? No current, right? If there is no current can flow into this entire stuff, right? Because nothing is connected. We are not taking VI because we are trying to figure out the impedance. Question.
If we are trying to figure out the impedance and there is a control source, there is a test.
Yes, this is the okay. So the reason I removed RL was because I was trying to figure out what is the impedance looking up. So RL was not a part of that that thought process. Otherwise, yeah, you should have an RL, right? So otherwise, so essentially we are trying to figure out what is the impedance on what is the time constant of the capacitor associated with the capacitor, right? So this is the capacitor. I'm trying to figure out what is the time constant associated with it. Which means I need to figure out what is the effective resistance attached. So one side is RL. That is pretty straightforward. What is attached to the left side? Left side is RD and something is attached to the top. So I need to figure out what is the impedance that is attached to the top. For that, I am doing all this tamasha. Right? Yes. So this should be, oh, sorry, this should be RD. Correct. Thank you. Okay. Make sense? Okay. So essentially now the impedance looking up, I mean here is infinite. So effective, if now I go back to this mother circuit. So effectively impedance looking on either side of the capacitor becomes, this side is RL, that side is RD, and that side is infinity. So what is the time constant associated? Right, so tau, this is C2, this was C2, right? Yeah, so tau 2 is C2 times RD plus RL, right? So when we have to size the value of capacitor C2, in order to ensure that the C2 behaves like a short circuit at signal frequencies, all we have to ensure is that this C2 times this time constant, essentially C2 times RD plus RL, is much greater than 1 over. Okay, so this is the constraint that comes from the output side of the amplifier. The constraint that came from the input side of the amplifier, or the constraint, was C1 times R1 parallel R2 should be much greater than 1 over omega naught. So now, as you see here, typically RL is not in your control because it will be a specification given to you, right? Omega naught will not be in your control because user would want certain frequency to be amplified. But the other things are in your control. You kind of C1, C2 is designer's choice, RD is designer's choice, R1 and R2 are designer's choice. So you kind of see you have a range of values for which you can satisfy whatever you want to do. Okay, make sense? Okay, so now let's see some of the problems that you might face, right? So one problem that you might face is this. Satisfying this constraint. So let's say for some reason, the designer, the requirement is RL is equal to 1 kilo ohm. Okay, so RD should be much greater than RL. So let's say you pick 10 kilo. Right? Now, what is much greater than is a question? No. Okay. So what is much greater than is kind of another. That depends on what type of error you can tolerate. But let's say, question. Can you repeat? I couldn't hear. Yeah. Her point is, since we are anyway thinking that RD should be much greater than RL, we can make a further approximation and get this to C2 times RD, which is in fact correct. You can do that. So, so the point that I'm trying to get at here is, let's say RL is 1K, RD is 10K, and we chose RD to be 10K because we wanted it to be much larger. Do you see an issue?
We were using RD to set the
Correct.
that case, we might not be in the consideration.
Excellent, right? So if RD is much high, what's going to happen? The Quiescent drop across RD is going to change. It's going to increase, right? So the drain voltage is going to increase. So for a fixed gate voltage, and if you keep on increasing drain voltage, your transistor might run out of saturation. Okay. So what is the fix for that? If you keep on, this is one question, right? In the mid-cell, keep on increasing RD, or in that case RL, what's going to happen? So if you keep on increasing it, it's going to get into linear region. But if I have to fix it, then what should I do? Increase VDD. Right? If I increase VDD and keep that voltage drop across R2 the same, which means I'm keeping VSG same, right? But then I have a provision of lifting the gate voltage. I can lift the gate voltage sufficiently to get RD, to get the transistor back in saturation. Okay, but as you see, this comes at a penalty. It comes at a penalty of using higher drain voltage or higher VDD, which means higher power dissipation. Right? For the same current, you are using higher power supply, V times I increases, so you burn more power. So almost always, power is the solution. If you can convince people to let you burn more power, you can almost get any spec that satisfied. But the key is not to use more power. Okay. So that will be a overarching theme of this course, and to figure out how to go about designing something without using high power supply. But at least at this moment we understand that using our high power supply has some benefits. Okay. Any questions? Okay, fine. So we have last 5 minutes. So before we end, so I'd like to change course slightly, and then I'd like to talk about another type of device, which is an NMOSFET device, right? So for those of you who have looked up the maybe Cedra Smith or Razavi's books, you will see that most of the treatments are using NMOSFETs initially, then they move to PMOSFETs. In this course, this time at least I have done the other way. So let's get back on track and try to also give you a flavor of what an NMOSFET device should look like. So when I say an NMOSFET device, it's even though it sounds different, but essentially for all practical purposes, they're exactly the same. So what was a PMOSFET device structure like? The base was a N-type semiconductor. There was a gate, and here was obviously there is an oxide in between, and we had doped these guys with P plus. And I mean, if we just mark this as source, this as drain, then we said that if we put a battery between gate and source where the gate voltage was lower than the source voltage, then there will be electric fields pointing in this direction, and there will be holes which will come, mobile holes which will gather here. And now if I apply some voltage between the drain and the source, there will be current flow, right? So this was essentially a PMOSFET device. An NMOSFET device is essentially exactly the same thing, just all the dopings are inverted. So you start off with a P-type substrate. Here you have the same thing, you have oxide and you have a gate. Here you have N plus. And let me still call this source. Let me call this source and this drain. And here, if you apply a voltage, a battery between gate and source in this direction, the way I have shown here, so there will be electric field from gate to the channel. And when you have electric field from the gate to the channel, you are going to get what? Electrons or holes? Electrons, right? So you are going to get electrons here, mobile electrons. Note that here the mobile electrons are the carriers of inverted polarity with respect to the bulk, right? So here in the PMOSFET case, the bulk was electrons, and the holes were giving you the channel, which was giving you the channel which can be controlled by the gate. In the NMOSFET device, the bulk is filled with holes, and you are developing a small channel of electrons by controlling the gate voltage or gate to source voltage. So in this case, the gate voltage has to be higher than the source voltage just because you want the electric field in the direction I have shown, right? So everything else is the same. Now, if I apply a voltage between drain and the source in the direction that I have shown, the electrons are going to flow from source to drain, right? So electrons are going to flow from source to drain. So essentially the current in this case will flow from drain to source. Okay, so that is the only difference, that the current flows from drain to source in an NMOSFET device. Current flows from source to drain in a PMOSFET device. Okay, so the constraint here becomes the turning on constraint in case of a PMOSFET device was VSG should be greater than some threshold voltage. In case of a NMOSFET device, it becomes VGS to be much greater than some threshold voltage. Okay. Similarly, the current equation, in case of a PMOSFET device, was current between source to drain was half mu P Cox W by L PSG minus this whole square. In case of a NMOSFET device, it will be IDS because the same current flows from drain to source, even though the carriers flow from source to drain. This becomes half mu N Cox W over L. Instead of VSG, it will be VGS minus this whole square. Okay, so this is N MOSFET. Okay, fine. So let's stop here. We'll carry on with the same circuits using N MOSFET in tomorrow's class.